In this lecture, I will give you differentiation in time and integration in time properties of Fourier series expansion. So we will start with differentiation in time, and let's say there is a signal xt and it is having the coefficient equal to Cn. The time period of signal xt is equal to t0, and as the time period is equal to t0, omega naught, the angular frequency, will be equal to 2 pi over t0. Now, if you obtain the differentiation of signal xt with respect to time, in this scenario, the coefficient will change to Cn multiplied to Jn omega naught. This is what you will get. So this is property number 9, differentiation in time. Whenever you differentiate the given signal, the coefficient will get multiplied by Jn omega naught, where omega naught is the angular frequency. Now I will explain its proof. The proof is very simple. First we will write the complex exponential Fourier series expansion. Signal xt according to the expansion is equal to summation n equal to minus infinity to infinity, coefficient Cn multiplied to e power Jn omega naught t. And now we will differentiate both the sides. On the left hand side we have dxt over dt, one time integration of signal xt with respect to time, and on the right hand side we will have summation n equal to minus infinity to infinity, differentiation of Cn e power Jn omega naught t with respect to time. Here you can see Cn is the coefficient which is dependent on n, so we can take it out of differentiation, and the only thing we need to differentiate is e power Jn omega naught t. And we know the differentiation of e power Jn omega naught t. I will first write down the differentiation after taking out Cn as a constant, and after this we will differentiate e power Jn omega naught t. Differentiation of e power Jn omega naught t will be equal to Jn omega naught multiplied to e power Jn omega naught t. You should know how to perform the differentiation, so I will not explain how we have obtained the result of differentiation. But if you have any doubt regarding the differentiation, you can definitely ask in the comment section. We have Cn multiplied to Jn omega naught multiplied to e power Jn omega naught t. Now compare this result with the standard complex exponential Fourier series expansion. Our signal is dxt over dt. This is the signal we are having, and in this expansion, if you compare it with the standard expansion, you will find Cn Jn omega naught t is the coefficient, and it is the coefficient of signal dxt over dt. So we can say dxt over dt is having the coefficient Jn omega naught multiplied to Cn, where Cn is the coefficient of signal xt. So I think the proof is clear, but there is one more point which we need to understand. What will happen if we differentiate signal xt 2 times? This means if we again differentiate dxt over dt, we have 2 times derivative of signal xt with respect to time. In this scenario, this will be the initial coefficient, and let's call it Cn dash. So Cn dash will be multiplied by Jn omega naught, or we can write Jn omega naught whole square multiplied to Cn. So differentiating the given signal 2 times, we'll have Jn omega naught square. In the same way, if we differentiate k times, then Jn omega naught will have the power equal to k. So this is the complete property which is known as the differentiation in time property of Fourier series. The property is very simple. You can easily remember it because you know how to perform the differentiation. Now we will move to the next property, which is the 10th property, and it is integration in time. First I will give you the property and then we will prove it. let's say there is a signal xt and it is having the coefficient equal to Cn. Again, we will assume t0 as the time period and omega naught as the angular frequency. Now if you integrate this signal xt, you will get the coefficient equal to Cn divided by Jn omega naught. So this is the property. And we know for the integration, we first change t to tau because we are interested in performing the integration from -infinity to t. This t is any instant of time, and to avoid the confusion between this instant of time and the variable we are having in the signal, we just simply replace t by tau. So tau is the dummy variable and we will have signal x tau, and it is integrated with respect to tau, which is the dummy variable. And whenever this happens, the coefficient which was Cn earlier will change to Cn divided by Jn omega naught. So this one here is the integration in time property, and now we will move towards the proof of the property. Again, I will first write down the Fourier series expansion. Coefficient is Cn multiplied to e power Jn omega naught t. Now I will replace t by tau. So we will have x tau equal to summation and equal to -infinity to infinity Cn e power Jn omega naught tau. Now we will integrate both the sides. We have integration -infinity to t signal x tau d tau. On the right hand side we have summation n equal to -infinity to infinity. Cn is constant, so it will be out of integration, and we need to integrate e power Jn omega naught tau with respect to tau. And we know how to perform the integration of exponential functions. I will directly write down the final result. Integration of signal x tau d tau from -infinity to t on the left hand side will be equal to summation n equal to -infinity to infinity Cn multiplied to e power Jn omega naught tau divided by Jn omega naught. So this is what we have on the right hand side, and again we will compare it with the standard Fourier series expansion. And after comparison, it is clear that integration of signal x tau is this signal, and here Cn divided by Jn omega naught is the coefficient. So this coefficient is the coefficient of this signal, and therefore we can write, if we perform the integration of the given signal, the coefficient which was initially equal to Cn will get divided by Jn omega naught. So this is all for the 9th and 10th properties of Fourier series expansion. In the next lecture, we will deal with the 11th property.